Hello, everyone. I'm Josh Turhan. I'm a rendering lighting supervisor over at Magnopus. And thank you to Houdini for inviting us over for this presentation. I want to talk about how we use Houdini daily on our AR/VR projects. And hopefully some of this stuff would be helpful for all the Houdini users out there. I wanted to actually mention a lot of the stuff, none of the stuff that I'm going to show is like pretty novel. It's a combination of all the GDC's talks that I watched over the years. So, I learned something from them, improve it, and hopefully, people watching this can take this, improve it, and then hopefully present it in another GDC talk or wherever. So it's a great community effort to grow the user base that way. So hopefully that helps. Just to talk about how we use Houdini. So this is some of the stuff we used Houdini for at Magnopus. So we did like fluid particle sims, procedural CD generation stuff, 4D capture processing, which I'm going to talk about. We use it for mesh decimation, which I'm also going to talk about. We use it for baking textures, point cloud import export, crowd sims, projection mapping. The point here is that it's just really, really flexible, and then it's like a Swiss knife, basically, of 3D tools, and we basically use it to do a lot at the company. And I feel like that's growing with the addition of like the game dev tools and everything that Houdini is doing these days. And today I'm actually going to talk about Bladerunner, Memory Lab, Coco VR, and another miscellaneous way of how we use Houdini to basically deliver these products. And I'm going to briefly talk about how we used Houdini to do all the Holocapture processing on Bladerunner, and then how we reduced all the assets on Coco VR. And then I'm going to talk about this hair tool that we developed at the end and open it for questions if we have time. So let me just start. For those who haven't seen Memory Lab, here's a brief trailer.
Memory extraction complete.
Welcome to your memory.
What are you doing? I'm no replicant.
You just retired him, which is totally against your training and your genetic profile. Something does seem off here. I knew it. You're in a different memory. Don't worry. You made me. I'll take care of you.
Right, so all the humans that you see in the experience are basically holocaptured assets, and we use Microsoft Holocapture system for that. So we shot for 2 days in Seattle, and I think we ended up with 49 shots and a lot of data. So Holocapture, for those of you who don't know, is a 360-degree 4D capture system. And it's basically, what's cool about it is they give you a semi-consistent mesh, meaning that the mesh topology changes every 20 frames or so, rather than every frame. And then, of course, it comes with the textures that are generated from all the cameras that you see in the screen here. So it's a really cool system to basically author all this really complex data to an MP4 that you basically just plug into the plugin in Unity or Unreal, and then it just plays back those cool humans that you see on screen. And another cool aspect of it is they deliver you an OBJ and a PNG sequence with the MP4 for you to be able to pretty much do whatever you want with those. So you can relight them, which is what we did on this project for the most part, and add some effects. And then let me talk about that. So here is how it all starts, basically. This is a very simple tool. We generated an asset, a Houdini digital asset, but it actually saved us so much time, so I just wanted to briefly talk about it. It's like a Holocapture import tool that we did. And the way it worked is you basically populate this. Let me play this. Oops. So right up top here, you have a Holocapture name field. And then all our files were in their specific folders named very consistently. So by just populating that field, we were able to literally like import any holocap with all the textures that come with it. So inside the tool, we basically, it's super simple. We have like an OBJ importer, and then we have a UV quick shade for all the atlases. And then outside the tool, you can like time offset it. But this tool saved us so much time because we had a lot of these to work with. And basically just by putting in the right spaces and right folders, we can import these really quickly. And the next thing we did with these holocaptures is we relit them. So, I mean, for those of you who know Bladerunner, lighting and color is a huge aspect of the franchise. So when we did the game, we wanted everything to live in the same world. And then relighting the holocapture was a really important part of that. Holocapture, as you saw, is shot in a very ambient and bright environment for the actual capture to work well. So you basically need to relight it, otherwise everything would just look out of place. And here's how we approach that. So through that tool, we imported the holocaptures, and just using very simple Houdini lighting, basically like an area light and an environment light, we were able to put these characters into their respective environments really fast. And then I don't have it shown here, but we had a cops session kind of running at the same time, and that imported the scene we had in Unreal for us to be able to visualize these characters right on top of the scene, so we could color correct in cops as well. I know not many people use cops, but it was actually pretty useful in this case. So we use really big area lights because unfortunately the holocapture geometry has some imperfections. So if you use like small lighting sources with a lot of shadows, it would really show up. And then the pop between the topology on every 20 frames or so is pretty visible if you do that. So we ended up using really big area lights with a little bit of an ambient light to kind of like fix the color differences between the HCAP and the Unreal scene. And then in here is another example of that actually. So this is the tech you see in the game a lot. And then in here we have like a really strong rim light on her. So we were able to use these really big area lights to really give like a rim lighting type of thing, which we couldn't with the tool itself. But we treat this as like spherical harmonics mostly rather than actual lighting, because like I said, we don't want really harsh shadows, otherwise the imperfections show pretty clearly. And here's like a raw scene that is just not lit. This is what comes out of the holocapture performance. We had blood at the end of that too. And then here's what it looks like when we actually light it. So this is what the textures look like unlit. And of course, this is what it looks like when we light them and bake all the lighting in. I mean, we had to process no, I'm not going to swear, but a ton of these things over the course of the project. So Houdini was super useful, treating these image sequences and colors or OBJ sequences like really efficiently. And we did a lot of these exporting processes on the farm actually, which saved us again, I'm not going to swear, a ton of time, basically. So another thing that we did for the holocapture stuff is, so we had to edit 2 different clips, one after the other. And of course, in VR, there's no concept of cutting, or editing really. It's just a continuous timeline. So to be able to switch between different takes, since she was a hologram in Bladerunner, we actually used this glitch effect, which kind of tied the 2 really different cuts together. And then here's how we did that. So this is basically, oops. So this is like the end of the first take, and this is the beginning of the second take. And then it basically needed to be continuous. So what we did is, for this clip, we turn that into a volume basically, so pretty much voxels all throughout. And then we used the points from volume SOP to actually create points where those voxels are. And then we spawn a bunch of boxes where those points are, again, fuse them, and then we booleaned everything together, divided it, so we ended up with triangles. And then we did an attribute transfer, so we could transfer the UVs from the original mesh to the boxes. Therefore, we ended up with this kind of unified mesh. And then the idea is basically like an MP4 glitch or something that you see with compression, but that works in 3D. And then, so that at the end, and then we animated some of the parameters too as the effect progresses basically. So in one frame, there'd be like, I don't know, 200 boxes that are bigger, and another frame will be smaller. So frame by frame, it looks like this. And when you actually play back the thing really fast, this is what it looks like. So you add sound effects on top of that. Perfect. That was our glitch effect. And the last thing I want to talk about, considering Bladerunner, is how we did these windshield wipers. It was a fun little trick. It's not that complicated, but at the end it worked pretty well. It was in the intro scene when the spinner kind of like goes through the city and there's rain and it's falling on the windshield. So the way we did that is, so I isolated the wipers themselves, and then isolated the geometry in the bottom of the blade and extruded that, converted that to a VDB here. And on the other side, I'm importing the windshield, and I'm spawning a bunch of points on that, and then I'm turning those to black pretty much. And here, this group, the group SOP has this really cool option to be able to group by a bounding volume, and that's what I'm doing here. So I'm basically using the VDB to isolate those points. And I'm coloring that white, and I'm here deleting everything that is not white. Pretty simple stuff here. But in the solver, what I'm doing is I'm basically adding the previous frame to the current frame, but in the attribute wrangle, I'm just multing down the color by like 0.1% or something like that. I think it's hard to see, but 0.95 there. And in the solver itself, there's a lot of sub-steps, so you don't get like stepping. So when you play that, it looks like this. Now on the other side, I am importing the windshield again, subdividing it, and then turning that black. And I'm doing a simple attribute transfer of the colors and blurring that and promoting that to a vertex color. And here in the simple baker, I'm literally just baking that to a vertex color, and I'm basically atlasing that to the 40 frames that are kind of spawning the whole effect. And this is what the map looks like. Oops. And then I'm basically using this as a mask for the shader inside Unreal. And that's how you get those like cool windscreen wiping effect, basically. That's the running blades effect. So on to Coco VR. Majority of Coco VR and how we used Houdini in Coco VR was decimation, because we would get, actually our technical lead on the project is here, and he used Houdini a lot on this project to be able to ingest all that data and basically put it into the engine. So I'll show you the trailer real quick.
Watch this.
All right, it's a super fun experience if you haven't done it yet. It's an Oculus, it's free. Like I was saying, a lot of project involved importing a bunch of assets, and I think Luke is really familiar with the scene. A lot of assets which were really, really dense from Pixar, and then basically making them run on real time. So that was the big challenge. And then we developed this Magna Reduce tool, which helped us basically go through a bunch of steps in optimizing the geometry. So here is what that entails. So the tool itself looks like, let me fast forward a little bit. So this is kind of the environment that we had to work with. And then for the most part, you were in the middle section of this environment. And this is also missing some of the ground and some of the assets around the ground. So for the most part, we had to kind of decimate what's around the middle section. And we developed this tool basically called Magna Reduce that allowed you to, so we knew exactly where you would be in the experience, like when you actually spawned around. So from that, we could derive what you will see in the environment. And then what we did is we basically had like these 10 points that we could define like in VR. Like you would look around and it's like, okay, this is a good point, and we would go to another point. And by populating the tool with those points, you knew exactly what to decimate. Because under the hood, I'll show you in a second, but what we're doing is we're like raycasting from those points out, and we're like constantly adding that to the points, the other points or something. And then we basically use that to determine what's visible and what's not visible. So that's like one portion of it. It's called occlusion culling, and another portion is delete by bounding box, which deletes like the smaller stuff. And then there's another portion, it's like straight up views, another tab that was a poly reduce, and it was basically just exposing the poly reduce parameters. So it's just like an overall tool to be able to optimize these things really fast. Well, I'll play this again. So that's kind of what the interface looks like. And then basically, I think we had like 10 slots, and you could go up and down depending on like how much you move in the experience. And then under the hood, it basically is, it's like this. So I think on the top level, you have all the poly reduces and the fuses, and then some other parameters as well. We actually added a really cool, it's not shown here, but we added a cool feature to the tool where on one side we had the poly reduce, and on another side it would do an instant meshes, the game dev instant meshes tool, and it would actually run it both on every geometry, and it would look at how optimized the geometry would look and how different it was in terms of, like we would have a VDB of both the solutions, and if the VDB was completely different, then we would choose the one that was closer but more optimized. So it could choose between instant meshes or poly reduce depending on how much it optimizes basically. So it was a cool way of kind of making it auto decide what was better. Because some geometry just straight up doesn't work with poly reduce, and sometimes, I mean 90% of the case it does, but sometimes instant meshes actually does a much better job. So here's like how we did the raycasting. So we basically create a sphere where those points are, and then we scatter a bunch of points on them, and then we ray that outwards using the normals of the sphere, and that basically just does a raycast on all the geometry that you will see from that point. And then of course, the more points you'll spawn, the more accurate this will get. And then below we had like two different ways of doing it. One was pretty aggressive. It basically just deleted everything that those points didn't touch. And the other one was like this. It was basically an attribute, attribute transfer of the colors. And it basically what it did is it got the geometry around what was also deleted. So it like minimized the errors basically. And here I'm basically just adding the results on top of themselves, or maxing the results, I guess, of all the different points. And at the end, you basically reduce a bunch of geometry, or you get rid of a lot of geometry that's not even seen from this view. So it's a pretty good way of removing what's not necessary, basically. As you can see here, like all the stuff in the back, we don't even see, or we're not even concerned. For example, that bridge, half of it was gone because we didn't even see it. So it was a really good way of optimizing. And here's another example of that, the ofrenda. And this was even a better case because we were basically not moving at all. We were in just one point. And here, the tool shows you how when you raycast from just like one point, how much you can actually remove. So this was before, and this was after. So again, really helped us. And from here, basically, after removing everything, it's pretty much everything's still visible from that point onwards, and then everything else is pretty much gone. So yeah, saved us a lot of draw calls and a lot of processing power, basically. So that's how we used Houdini, on Coco. And then the last thing I wanted to talk about is this hair tool that we developed. We didn't end up using this on any projects because we didn't end up having any hair, but hopefully on a future project we will. This was a really fun thing to do, and I want to again say that a lot of the techniques I've used here are actually derived from techniques that I've learned just by watching GDC talks. So some of the stuff is probably stuff that you've already seen, but it differs, I think, from other examples at the end, and I'll show you why. So this was a Chewy asset to demonstrate it that we got from Turbo Squid. And then in here, actually, it came with grooms or groomed hair. So I'm basically doing the hair grooming steps that you would do, convert to VDB for collisions, and then use the skin. And in here, I'm importing the curves that came with the actual asset from Turbo Squid. And this is my basis for all the ribbons that I'll end up generating to be able to export to the game engine. And I'm basically just isolating what I need. Like the body is a different set, the face is a different set, the head is a different set. By doing that, I was able to work on different parts of it without crushing the machine. So in here, I'm basically running it through the groom process. I think the grooms nodes in Houdini are like amazing right now, so I would definitely recommend using those. In here, something different that I did is I basically took the original curves and I created a main clump parameter on each primitive, which I ended up using all throughout. And that helped a lot because I knew exactly like what primitives were which clumps. And here I'm sort of visualizing that parameter through a color. Let me show you. Oops, not too far. So yeah, here is what like the main clump parameter looks like when it's randomized on all the different hair curves. I'm running the hair through like your basic groom stuff that you would do, the clumping, the waves, the displacement, the frizz, the fur, everything. And in here, then I turn, that's how I export the hair. And here, in another separate node, I'm turning those into ribbons. And that's how I did is first I'm importing the curves, the whole hair. I'm turning the UV parameter into color, which is just 0 to 1 from hair to tip. I'm sorry, from the tip to the root, which is super useful. And in here, this is again something a lot of people do. I'm importing the VDB and I'm smoothing it, and I'm adding normals to that. And this defines how the ribbons basically flow across the surface. And I'm transferring those normals to the curves here, so I can use the hairs to generate those ribbons. And under the hood, I'm still retaining all those like main clump attributes and main curve attributes. So, and in here, you can see how that all kind of works out. So per clump, I am, this is the end result. So this is the ribbon and the hairs kind of working together. So per clump, I'm basically isolating the clump. And then here I'm choosing one of the curves and another curve that is a little farther from it. And between the two, I'm blending them to get like an average of the curves. So I like take the two extremes and then kind of lurk between them to get a generalized curve of the clump itself. And then I'm extending the curve so the ribbon is a little longer than the actual clump of curves. And here, so using that normal that I imported from the surface, I'm basically moving the curves apart from each other. And I think I'm doing a poly patch on it, and then I'm lofting them together and creating UVs on that. And here I'm bringing in the main clump attribute again so I can isolate them together later on. So that's essentially how it works. And at the end, when you run them all, you end up with something familiar, a bunch of ribbons to export to the game engine. And this is where I would actually, the step that I don't show here is I stack all the UVs actually. So I don't work with just one UV for all the and this is where it differs actually. So I basically stack all the UVs, so I end up with hundreds and hundreds of UV shells that are all separated for each ribbon. And so the next part then is, go quickly. So I import the hairs again, and I again work on a cluster. I'm sorry, a clump. And this is how that works. So I isolate the two together. And I'm actually, okay, so here I'm raying the curves onto the ribbon. And as I do that, I record how far the curve was from the ribbon. And I also transfer the UV attributes from the ribbon to the curves. So we end up looking with like a super flat result like this. And in here, this is how I record all the distance attributes, distance from the ribbon. Plus I have a randomization attribute going on. I have the colors that are basically grabbed from like the main hairs that ended up being in the CD. And then in here, since I recorded those UVs from the ribbon itself, I just use that to define the position of the hair now. And then I ended up with a really small portion in a UV space, 0 to 1 UV space per clump. So when you add all those together, you ended up with something like this. So it's pretty much all the ribbons on the head as a UV shell. Of course, this is very expensive. This ended up being a 4K map that I exported. But the results are really good because you get some really cool, let me show you the results. Oh yeah, and then here I record like your usual suspects, which is a tangent attribute. And this is where I record the distance, which Unreal's hair shader loves, and then the 0 to 1 attribute, and then a random attribute that all gets fed into the hair shader. So this is the result. You end up with like really good detail in the hair itself, since every clump is slightly different, and every clump is basically a representation of the actual hair. You end up with this like super complex looking result. Of course, it'll be awesome if this moved, but by the way, please disregard the face because I don't have any hair on the nose or on the mustaches or anything, so that's why it looks super weird. But the hair on the head is what I kind of exported, and this is what the map looks like. So just a bunch of hairs basically rendered from that orthographic camera inside Houdini that I exported. It actually took only like 2 minutes to render since I wasn't doing any shading. It was just constant colors. And yeah, this is the result. And hopefully this will be something that people can use in the future. Of course, I think we can do with a lot less ribbons at the end. I think this was a little overkill. But yeah, that's very art directable. So open for any questions, if anybody has anything. Yes, please.
For the raycasting deleting geometry, do you delete primitives or do you delete pieces that
We treat it as polygons, so we deleted polygons instead of pieces. I think for really big worlds, if you have stuff that's outside, you can treat the far stuff as like bounding boxes even. So delete everything that's a bounding box if you have a lot of geometry. But we ended up treating it per polygon, so we were actually deleting polygons. Yeah.
For the Coco stuff,
Yes.
did you just receive like traders for them as well, or did you guys take all that down during your destination?
So we received 360 captures of the environment. So we basically gave them a bunch of positions to render from. And then in VR, we basically built a shader that would switch between, we projected from those points, but it would blend between those different spots like seamlessly. So it looked like it was a continuous space. Because we didn't want to mess around with their look. You know, it was so beautiful. It was so well lit. And it was like very well done.
It doesn't seem like that's happening when you watch the footage.
Right.
It's like it's all
Yeah.
retextured.
Yeah, it also helped with optimization, obviously. You know, performance was great just because we were just using textures instead of... Yeah, exactly. Cool. I guess that's it. Thanks for listening. Thanks for coming. Hope it helps.